we're only going to need uh, these like this and the first like column for this formula sheet, right? So what we're going to do today is we're going to go like one by one, right? We're going to create your own formula sheet, right? Since this is going to be like an open notes exam, might as well take advantage of its open notes nature, right? So we're going to go one by unit, right? And we're going to address common equations that we're going to need, just common things that we're going to need knowledge of for the exam. Okay. So the first one that we're going to work on, obviously, is going to be our kinematics. Okay. So section 1 will be kinematics. This is the equations that we're going to need to know, right? So there are several equations that are very, very important when it comes to kinematics. Okay. The first one is this, right? So velocity is equal to distance. Oops, let me distance over time. So right now, guys, I would urge you to like have a notebook out just to make your own formula sheet. Like I'll send this to you guys later, but like, you know, have a separate sheet, right, on like a notebook or a piece of paper where you have all of these formulas in, just so it could fit your needs, right? So this is a very important equation. Velocity is equal to distance over time, right? That's the basics of kinematics. But we only use this equation in what instance, right? So I'm going to ask this question. I want you guys to type out an answer. When do we use this equation, right? In what instances do we use this kinematics equation? Velocity is equal to distance over time, right? Type out an answer. When do we use this? I mean, there's motion all the time, right? Okay, we're calculating horizontal velocity and velocity is constant. Okay, so that's very, very important, right? So a lot of the times, Cedric is right. A lot of the times, for projectile motion problems, right? For projectile motion problems, velocity is going to be constant, right? So if you're thinking about like an object moving, in like a projectile motion like fashion, right? You know that there's going to be a force due to gravity going down, so it's going to accelerate, or in this case, decelerate in its vertical motion. But there's nothing affecting it because we're gonna assume air resistance doesn't exist, right? There's nothing affecting it horizontally, meaning there is no acceleration, right? If there's no acceleration, there's no change in velocity. So Eric's right. We only use this equation when we're talking about zero acceleration, right, or no acceleration. So this only applies if there's zero acceleration or like constant velocity. Okay, so this equation only applies when there's zero acceleration or when there is constant velocity. Okay, the other equations, right? So when acceleration is not zero, when there is a changing of velocity, right? We're going to use other equations. We're going to use our three kinematics equation, right? So the first one is VF is equal to VO plus AT, right? So VF is final velocity. VO is initial velocity. Acceleration A is acceleration, obviously, and T is time. Okay, so we're gonna write our actually let's do other ones. Change of x is going to be our displacement. Oops. Displacement. Okay, so we have VF equals VO plus AT. We're going to have change of x or displacement is equal to DOT plus 1/2 AT squared. Okay, we're also going to have VF squared is equal to VO squared plus 2A change of x. So these are going to be our kinematics equation, right? When there is acceleration. When acceleration exists, these are going to be our equations that we're going to need to use. Okay? Pretty simple stuff. Okay? So the things to know here, right, is the idea of just algebra, right? So remember in kinematics, as long as we know like 3 of these things, right, we know everything else. Okay, as long as we know 3 things, we can apply it to these equations and we can find our missing variable pretty easily. Okay. Another important thing is let's go back to what Sergio said when we're talking about projectile motion. Okay, so projectile motion is when the object is not just moving at one dimension, right? It's not just moving left, right, or up and down. It's moving left, right, up and down at the same time, right? It's moving at two directional way. Okay, so projectile motion is when it's moving in when it's like in the air, right? It's moving left, right, or horizontally and vertically at the same time. So horizontally and vertically at the same time. So again, this is very important that you guys like probably rewrite this on a separate sheet of paper, just because my handwriting is so bad, right? So horizontally and vertically at the same time is when it's projectile motion. So we're going to typically, and I want you guys to remember this, typically when we're talking about a horizontal or a projectile motion, we're going to split up the problem vertically and horizontally. Okay, so vertically, acceleration is due to gravity. So we're typically going to use like the three kinematics equation. Horizontally, we're going to have no acceleration, right? Assuming that there is no air resistance, right? No acceleration, so we're going to use velocity is equal distance over time. Okay, so those are very, very important things. Also, when it comes to kinematics, right? When it comes to kinematics, we have like vectors are going to be super important. So the concept of vectors, right, is when there is a motion and an angle. Again, it's moving left, right, up, down, or horizontally and vertically at the same time, right? So a lot of these problems, we can't really do things when it's like at an angle, right? So let's say this is like a 30-degree angle. It's really, really like hard to work with a problem with this velocity. Let's say this is 2 meters per second. Okay, so a lot of the times, right, since we know vertical, we know what to do with vertical, and we know what to do with horizontal, what we're going to do instead is like, hey, let me just separate out this this vector, right? So we're going to separate it by its vertical axis and horizontal axis. Vertical axis, remember, is sine. Horizontal axis is cosine. So to figure out this, like the vertical component of this or the horizontal component of this, we just use our sine cosine function. So vertical velocity will be 2 sine of 30 degrees. Okay, and make sure the calculator is in degrees, right? And the horizontal velocity will be 2 cosine of 30. Okay, so that's very important to work out. And then now we have our initial vertical velocity, and then we have our horizontal velocity. Okay, so now we can do several things to be able to solve for this problem. Another important thing to need to know, like when we're tossing an object up and down, right? We're going to need to know, right? And let's talk about vertical velocity. When we're talking about vertical velocity, so let's say an object is going up, right? And it's going to go here. Okay, so one important thing here is that the velocity here, okay, the velocity at this point will be 0. Okay, so we know acceleration, so we're giving it an initial velocity when we're throwing something up. It's going to slow down, slow down, slow down, slow down until it hits the top, where we'll have a vertical velocity of 0. This is because gravity is, again, slowing it down. And then when it reaches the top and when it's going down, it's going to speed up, speed up, speed up until it hits, the ground or wherever you throw it from. And then the velocity here is equal to the velocity here, right? Like if you throw something up, when it lands in your hand in the same position, it's going to have the same velocity as when you throw it up. Okay? So that's very important to understand. And that's like the basics of kinematics, at least like the equations that you're going to need to know for kinematics. Okay, so now let's move on to the next part, right? So the next part of physics is going to be forces, right? Forces and dynamics, right? Forces or dynamics. Okay, so now it's not just about like motion. Now it's about like the forces that we apply on objects, right? So there are several different types of forces, right? There are going to be contact forces and non-contact forces. Okay, contact forces, there are several, right? There's several for contact forces, and again, contact forces are forces that requires contact, right? When you're pushing something, when you're pulling something, those are contact forces. Okay, so things like tension, things like pulling force, right? Like when you pull something or when you push something, things like friction, right? All of those things are contact forces. Non-contact forces are forces that require no contact, right? Things like gravity, electrostatic forces, and magnetic forces, right? So, or electromagnetic forces. So all of those things, or just like nuclear forces and stuff like that, are non-contact forces. They don't really need like something to touch for the force to happen, right? Gravity is a perfect example of that. You know, it's not like there's a hand pulling you down to stay to keep you on Earth. It's an invisible force. It's a non-contact force that's pulling you down to keep you on Earth. Okay. So what's important about forces is the idea of what it does, right? So what forces does, and this is summarized by Newton's laws of motion. So what's important about forces is what forces does. Okay, so remember Newton's first law of motion. Newton's first law of motion is an object will stay in motion, right, at the same velocity unless acted upon by a unbalanced force, right, or by a net force. Or an object will stay at rest unless acted upon by an unbalanced force. Okay, so the idea here is that forces causes, not but equal, causes acceleration. Okay? So forces causes acceleration to happen. It forces the change in velocity either from 0 to 1, or from 1 to 0, or from 1 to 2, right? Forces will cause acceleration to happen, right? And this is summarized by this, right? Force is equal to ma. So what needs to happen if there is a net force, right? If net force is not 0, then there is acceleration. Okay? If there is no acceleration, that means there is no net force, meaning the forces on the left, on the right, cancel each other out. Okay, so this is super important to understand, right? A net force causes the acceleration. Again, if there is no net force, there is 0 acceleration. Super duper important to understand. Okay, so these are I guess the force equation. Like this is the force equation, right? So the important thing about forces, right, is the free body diagram. Okay? So the free body diagram, okay, is typically something, you know, you can draw a circle, you can draw a dot, you can draw a box, you can draw anything you want, but just make sure that you're applying these forces properly. Okay, so in a free body diagram, what we want to do is we want our forces in an axis, right? We want the forces either in the horizontal axis, let's say pulling up, pulling down, and the vertical axis or horizontal axis, going right and going left. Okay, so what we're going to do, and this is super important, we're talking about forces, we're going to, again, this is super important, this is pretty much like the entirety of physics, is that we're always going to split up our problems by the axis, right? Split up by the axis. Okay, so horizontal, right? Horizontal forces are by themselves, and vertical forces are by themselves, right? So we're not going to like work with a horizontal force and a vertical force. That's not going to happen, right? We're only going to work with this set of forces by themselves and this set of forces by themselves. Okay, super duper important to understand. I repeat, that is extremely important to understand. We're going to always split up our forces by their respective axis. Okay, so let's draw something, right? So let's say there is going to be normal force, right? There's going to be mg, and there's going to be like some applied force going up, right? So force applied vertically. Okay, and then let's say there's going to be a force going this way, force of friction, and then let's say there's going to be a force going this way, and this is going to be a force applied horizontally. Okay, so what we're going to do with this problem, right? So when we're, again, the important equation that we have in kinematics, in forces or dynamics, is sum of forces is equal to mass times acceleration. Okay, so first, again, this is important. We have to split them up by axis. We're going with horizontal and vertical. So let's again just split up by horizontal and vertical. So let's do our sum of the forces, or our net force horizontally, right? Our net force horizontally. So our only forces horizontally is this force applied and this force of friction. Okay, and we know that they're going in opposite direction, right? So since we know we're going in opposite direction, they're going to have opposite signs. So if we make right positive and left negative, this is how it would look like. Force applied horizontally is equal, or sorry, force applied horizontally minus force of friction. That's going to be our sum of the forces, right? It's going to be this force minus this force because they're in opposite direction. When we're talking about vertical forces, they're going to be different, right? We're going to have three forces that we're working with vertically, right? And again, these forces are in an opposite direction as the force of gravity. So if we're going to do some of the forces vertically, we're going to make up positive and down negative. So force applied vertically plus normal force minus gravity. Okay, so that's going to be our sum of the forces here. Okay, and then again, this is equal to ma. This is equal to ma. Okay, super duper important. A lot of the times, right? So we're going to have a problem where like something's being dragged on the floor. A lot of the times, like as example, like the vertical motion, right? There is no vertical acceleration. If there's no vertical acceleration, that means some of your net force, right? If A is 0, your net force will be 0, and then they would equal like this: force applied horizontally minus force of friction, and then you're going to solve for it by force applied horizontally is equal to force of friction. And that's just algebra, right? But that's only when, right, there is zero acceleration, when there is either constant velocity or when the object is not moving. And in those instances, you make your sum of the forces equal to 0. That means that your forces going up and your forces going down are equal to each other. But again, that is only applied when either the object is at rest or when the object has a constant or an unchanging velocity. Okay? So super important. And that's like the basics of it, right? So this is going to be the basics of forces. Super, super easy. I guess let's do like another one. Okay. So what happens when we have an object being pulled by an angle? Okay. So let's make this 45 degrees. Okay. So when we have a force applied at an angle, okay. Again, we are going to have normal force. We're going to have mg, and we're going to have force of friction. Okay. So let's say we have something like this, where we have the force applied, right? When we have the force applied in an angle. Again, this is super important. We were told, right? I told you guys to split up the forces by the respective horizontal or vertical axis. Well, we have a force applied here that's neither vertical nor horizontal. It's both, right? It's both horizontal and vertical at the same time. So what that means is we have to make sure that we split this up, right? We split this up by the right axis, right? We're going to define, instead of like working with this force applied, we're going to split it up into its two components, the vertical axis and the horizontal axis, right? And then we can easily work with the splitting up of our forces or by their axis. So again, we change this by our sine and cosine component, right? Vertical is sine, horizontal is cosine. So we're going to have force applied, right, vertically is a sine component. So it's going to be force applied times sine of 45. Okay? The force applied horizontally is the cosine component. So it's going to be the force applied cosine of 45 degrees. Okay? So now what we're going to do, since we split up these forces, this is going to be the vertical force, this is going to be the horizontal force, is we're now going to redraw the free body diagram. Make sure that you always draw the redraw the free body diagram from this point. Okay? So we're going to have, so this is split up, so it's force applied horizontally, right? There's going to be force of friction. There's going to be normal force, and then there's going to be the vertical component, force applied vertically, and then again gravity. Okay, so now we see them in its verticals and vertical, horizontal and horizontal. Now we have split up this problem by its vertical and horizontal axis. Now it's pretty easy to work with. Okay, so again, the really important equation here is this one. Sum of the forces is equal to ma. Okay, another thing, okay, you might see something like this is going to be an inclined plane problem, right? So we're going to see this quite a bit, right? Inclined plane problems. So the problem here, right, is our axis becomes different. Okay, so our axis becomes different because the motion is no longer horizontal or vertical, right? Now it's in an angle. Okay, so let's say this is like let's stick with 30 degrees. So this is where the problem of like axis becomes a little bit different. It's because the motion here is no longer just left, right, or up, down. Now it's going to be in an angle, right? And this is the inclined plane problem. So what we're going to do is we're going to change up our axis, right? Instead of going by our general vertical and horizontal axis, we're not going to do that, right? Our axis is going to be different. It's going to be, we're going to make this our horizontal, okay? And then we're going to make this our vertical. Okay, so super duper weird, right? We're going to make the axis that goes along, right? That goes along the slide horizontal, and the axis that goes along like that pushes out of the slide, right? Or pushes into the slide as our vertical. Okay, so we're going to kind of like rotate our axis, right? Instead of a proper vertical and a proper horizontal, we're going to rotate our axis. Okay. So what's important here is going to be the forces that we split up. Okay. So a lot of the times, right? So we know that this object is going to slide down. It's super duper important. I'm going to redraw it, but it's super duper important to know that this object is going to slide down. So my question is, why does this object slide down? Okay. Why does this object slide down? Why is it if you get on a slide, why are you accelerated and slide down? I want you guys to type in an answer. Okay, gravity, right? So gravity is going to pull you down. But it's super duper important that you guys understand, right? Or that you guys know that gravity is always pointed. Where is gravity always pointed? Okay. Where is gravity always pointed down, right? It's always pointed in the right down direction. So you know that gravity is always pointed down. But hey, right, since gravity is pointed down, it's no longer in the axis that we want to work with, right? It's not in the axis going down the slide, and it's not in the axis going into or out of the slide. Okay, this vector of gravity is in an axis that we don't want to work with. Okay, so typically what we're going to split up here, right, is not going to be force applied. Typically, sometimes we will, but it's going to be gravity. We're going to split up gravity into its right slide component and this component. Okay, so remember, always sine goes with slide. Okay, so this component that is going down the slide is going to be the sine component, and the one going in here is going to be the cosine component. So this is going to be mg sine of theta, and then this is going to be mg cosine theta. Okay. Another important thing, super important that I forgot to mention, is normal force, right? So normal force is super cool. So the idea of like normal force is that for like is typically when there's a surface, right? Normal force, we typically use it when we have a surface. So normal force is the force applied to a body or to an object by the surface it's on, right? So right now you're probably sitting on a chair, right? The reason why you and you know that gravity is pulling you down, right? The reason why you're not going down is because gravity is holding you up. Okay, so assuming this is you guys, okay, and this is a floor that you're on, that you know that gravity is pulling you down. But remember, if the net force is not zero, that means there's an acceleration. But if you notice here, you're not going down the ground, you're not falling, you're not like moving downwards, right? You're staying still. It's because there is an equal force that's being applied to you going up, and that force is normal force. Okay, super important. And in this case, right, since there's no acceleration, the sum of the forces is equal to 0. So that means your sum of the forces is equal to n minus mg, and then that's going to be 0 is equal to n minus mg, and that makes n is equal to mg, right? So a lot of the things is like n is equal to mg, and then you can work with it that way, right? So that's super duper important to understand. Is that the normal force is the force applied by the surface. Okay. Another important thing is the force of friction. Okay. So the force of friction is super, super important. The force of friction is, remember the fun equation, right? This is the coefficient of friction. And this is normal force. Okay. So if you notice here, right? If you notice here, the heavier you are, right? Like the heavier the object is, right? The bigger mg is, the bigger n has to be, right? The bigger the normal force has to be to lift you up. And if you notice, if you're trying to like, let's say you have like a light box and a heavy box right next to each other, and you're trying to pull both boxes across the floor, right? Obviously, the heavier box will be a lot harder to move, will be a lot harder to accelerate. The reason it's harder to accelerate is because the force of friction for the heavier box is larger. The force of friction is heavier because if mg is larger, normal force is larger, right? If normal force is larger, the force of friction is larger, right? For the lighter box, mg is small, that means n is small, and if n is small, that means force of friction is small. Okay? So that's the basics of I guess like friction, right? The force of friction. Let's see what else. Okay, so we're gonna have like two types of frictions. We're gonna have static friction and kinetic friction. So static friction is the friction that is when the object is at rest, right? So for example, you're trying to pull you're trying to push the heavy box, right? But you're not strong enough, and the heavy box is not being pushed, right? It's not being accelerated, right? You're applying a force, right? But the static force is too much to overcome, right? So it's not going to move. So again, static friction is when the object is at rest, right? Or not moving. And then kinetic friction is when the object is moving. It's also very, very important to understand, right? And I don't know if you've ever felt this before, but when you're trying to like push a box, right, or push something that's really heavy, right? I don't know if you've noticed, but the initial push, right, is going to be very, very hard. Okay, but once you start moving the object, it becomes pretty easy or becomes easier, right? So what that means is that static friction is typically larger than kinetic friction. Okay. The static friction is typically larger than the kinetic friction, right? It is harder to move an object, right? The force of friction will be stronger when you're trying to move an object than it would be once the object is already moving, okay? Just, little things that you need to understand, okay? So, pretty sure that's it for forces. So, let's talk about momentum, okay? And in this case, when is kinetic friction larger? It's not, right? Kinetic friction is not going to be larger. Okay, it's going to be static friction is always going to be like more to overcome. Okay, so now we're going to do momentum. Okay, so momentum is the idea of like, it's kind of like inertia, right? So the inertia is like, it's how hard it is to move an object or how hard it is to stop an object, right? That's what momentum is, right? Again, you're not afraid of like, let's say a ping pong ball moving straight to your face, right? You're not that afraid of it, even if it's moving very, very fast, because the mass of it is very low. Okay, but you are afraid of a moving car because the moving car's momentum is a lot higher. Okay, so that's the idea of momentum, is that mass, right? Momentum is mass times velocity. That the concept of mass and velocity affects momentum, right? The bigger the mass, the bigger the momentum. Bigger the velocity, bigger momentum. Okay, so that's like the basics of linear momentum. Also important to understand, we have the law of conservation momentum. Okay. And what that means is that momentum is always conserved, right? The amount of momentum doesn't change from one to another. Okay? It does not change from one to another. Okay? So the momentum before and the momentum after are going to be equal. Okay? So no matter what happens, the momentum before, the momentum after is always going to be equal. Okay? So concepts are, let's say when we have an object moving at like, let's say this is a 2 kilogram object moving at 3 meters per second. And let's say we have an object here. Let's make this 3 kilograms. And then this object is at rest. So that means it's at 0 meters per second. Okay. So let's say we have like 2 objects. And this object is going to keep going to the right until it hits the 3 kilogram object. Right. So they're going to collide. Momentum typically deals with the concepts of collisions. Okay, so let's say that this 2 kilogram object is going to collide with this 3 kilogram object, right? And assuming that once they collide, they're going to stick together and move together right after the collision, right? So the collision after. Okay, so this is before. Okay, so the collision after, they're going to be moving together, okay, to the right. Okay, so the question here is at what velocity will they be moving at, right? So if they're going to stick together after the 2 kilogram object bumps into the 3 kilogram object, and they're going to stick together, at what velocity will these two objects be moving at? And we know that these two objects will be moving together. Okay? That's super duper important to understand. These two objects will be moving together. Okay, so again, this is super important to understand the conservation of momentum. Momentum before, momentum after is going to be different. And we know momentum is equal to mv. Okay, so we know the momentum of the 2 kilogram object. So we're going to do before first. The momentum of the 2 kilogram object is going to be 2, right? Or 3 times 2, sorry. 3 times 2 because, or 2 times 3, let's go with that. 2 times 3 because the mass is 2, so m is 2, and then v is 3. Okay, so the momentum of the 2 kilogram object is going to be 6. And the momentum of the 3 kilogram object, again, it's mv, so 0 times 3, that's 0. Okay, so the momentum of that is going to be 0. Okay, so let's do 3 times 0. Okay, so the momentum of the system before is 6. Okay, super duper important. The momentum of the system before is 6. So the momentum of the system before is 6. You have to know that the momentum of the system after also needs to be 6. Okay? Because the idea of the conservation of momentum. Right now, and it's super important to understand, since they're together, since they stuck together, we can treat this object as as one object, right? And we can treat it as having a mass of 5, because 2 plus 3 is 5. So now the momentum of this is 5, right? So the momentum after is going to be the mass of the two objects, which is 5 times the v after, right? So we're going to solve for the v after. We know the momentum has to be 6 because momentum is conserved, right? And then now we can do our problem, right? We can solve for VA, and it's going to be 6 over 5, okay? Or it's going to be like 1.2 is equal to VA. That's the basics of momentum. Okay, but these is when the objects like sticks together. So important things to know about momentum, okay, super duper important things, is the different kinds of collisions, right? There are several different kinds of collisions. We have elastic, and perfectly. Inelastic collisions. Okay, so these are 3 different kinds of collision. Again, inelastic, elastic, and perfectly inelastic collisions. Okay, so it's super duper important that you understand that elastic collisions is when they stick together. Oops. When objects stick together. That's an elastic collision. And an inelastic collision is when the objects don't stick together. Okay. It means like they either bounce off in one direction or the other, or like one is going to move faster going to the right and the other one's going to be moving slower also going to the right. But inelastic is the objects don't stick together. So perfectly inelastic is very similar to this, right? It is an inelastic collision, but perfectly inelastic collision is when the kinetic energy is conserved. Okay. So in all of these, the inelastic and elastic collision, right, in the first two, kinetic energy is not going to be conserved, right? So the differences between the kinetic energy before and the kinetic energy after is going to be different. Okay. It means that the kinetic energy or part of the kinetic energy from before is going to be okay. So the units for momentum is just kg meters per second. Okay. That's the units. Okay, so kinetic, again, it's super important to understand. For inelastic and elastic collisions, kinetic energy is not conserved. Okay? Ke not conserved. So again, that means that the kinetic energy before and the kinetic energy after is going to be different, right? It means that there's going to be some loss, quote unquote, of kinetic energy, right? It means that kinetic energy will be like part of the kinetic energy will be transferred into other things. Okay, will be transferred into other things, whether it be like heat or whether it be friction, but it will be transferred through other things. In a perfectly inelastic collision, the kinetic energy has to be conserved. Okay. And again, this is super important, and I've said this when we talked about momentum in the lecture from before, is that a perfectly inelastic collision does not happen in the real world regularly. Okay? Perfectly inelastic collision does not happen in the real world regularly. Right, yeah. It doesn't happen because kinetic energy is rarely conserved, right? So when we're playing billiards or pool, right, and we have the two balls hitting each other, right, there's going to be some energy loss either through sound or through like friction, right? So it's very hard to keep kinetic energy conserved. So it's very hard to have a perfectly inelastic collision. Now, my question is, and we talked about this before, when, right? When is a perfectly inelastic collision possible? In what instances is a perfectly inelastic collision possible? Okay, I want you guys to see. If you have an answer, please type it out. In what instances is a perfectly inelastic collision possible? Not exactly, right? There'll be a lot less, but not exactly. Okay, there'll be like a lot less loss just because there's no like sound, right, to like transfer to, but there's still going to be like friction, some energy loss due to friction. Okay, in what instances, right, is a perfectly inelastic collision possible? And we've talked about this before. No, like when there is no Ke loss, right? Perfectly inelastic kinetic energy is conserved. So, like, what instances is like the amount of kinetic energy going to be the same before and after the collision, right? So that's what I'm looking for. In what instances is that possible? No. When they stick together, there's going to be kinetic energy loss, right? So in an elastic collision, actually, there's going to be a lot. Kinetic energy is going to be lost, right? A lot of it is going to be lost. Nope, not exactly. Well, no, not exactly. So I'm saying that it's almost impossible in the real world, right? So I'm asking for in the real world, right? When is it possible? When one stops and another keeps moving, it really would depend on like the mass and the velocity of the two objects, right? Like that would not necessarily be the case. Okay, so let's, I guess like I'll tell you guys now. So this is only possible in the atomic level. Okay, so meaning like in the very, very like quantum level, in like the small, right, in the small world, right, with like atoms and molecules and stuff like that. That's the only way. That was the only way a perfectly inelastic collision is possible, right? When kinetic energy is conserved. But a lot of the times, and this is going to happen, a lot of the times, like in the problems that you might see in the AP exam, we're going to get like hypothetical, perfectly inelastic collision. And that's fine, right? But it doesn't typically happen like in the real world. So another thing about collision is like they might ask you, right? They might ask you about a collision. Is it a perfectly inelastic or okay, sorry. Is it going to be an elastic or a perfectly inelastic collision, right? So what's important there is you're just gonna have to find the kinetic energy before and the kinetic energy after, right? If they're the same, you know it's going to be perfectly inelastic. If they're not the same, you know that it's going to be one of these two things. That's it. Super important. Okay. So next we're going to talk about energy. Okay. So again, energy. Important thing about energy is that we have the conservation of energy, meaning energy is conserved, meaning the total energy before and the total energy after is going to be the same, right? Total energy before, total energy after is going to be the same. Okay? So let's look at like when that's possible, right? So we know that the total energy is whatever energy the system has to begin with, right? So when let's do something like this, right? Actually, let's do okay. So let's do something like this. Let's say like it's like a half pipe, right? So here, right? Let's say there's a skateboarder here, right? There's a skateboard here. We know that it's going to like slide down and then go back and forth, back and forth, back and forth, right? And so assuming that like again there's no friction, right? Assuming that this object is at rest, right? Assuming that this object is at rest, what type of energy does it have? Okay, what type of energy does the system have? Please like type an answer. Assuming that this is at rest, it's going to have good. It's going to have potential energy, right? So the energy here of the system, right, before is just going to be potential energy. Okay? And we know that's the potential energy because it's going to have a height, right? As long as it has a height, we know it has mass or a height, we know it has potential energy. Okay? So we know potential energy is equal to mgh. Okay? So now let's say the skateboard slides down, right, and hits the bottom, right? Or not hits the bottom, but is at the bottom. Once the skateboard is at the bottom, right, we know that, hey, it no longer has a height, right? Because now it's on ground level. There's no longer height. Now there's no longer, right, potential energy. If there's no age, there's no potential energy. So the total energy, okay, at the, I guess, let's say bottom, is going to be just kinetic energy. Okay? And kinetic energy is based on mass and velocity, 1/2 mv squared. Okay? Another important thing, what if, right, this object is right here? Okay? What if this object, right, it still has a height. It might not be a big height, but it has a height. Let's name this h2. Okay? Now it has a height, and now we know it's moving. So not only does it have potential energy, but it also has kinetic energy, right? So let's say TE middle, put M, okay? It's going to be a mixture of potential plus kinetic energy. Okay? That's the basics of it. But very, very important to understand is that all three of these total energies are going to be equal, right? Since energy is conserved, the energy at the top, the middle, and at the bottom is going to be the same. Okay? So super duper important. So now, what if, right, this object goes past, right, goes past the middle, right, goes past the bottom, goes past the middle, and tries to go to the other side? Okay, where does it stop? Or yeah, where does it stop on the other side? What is the maximum height does it get to on the other side? Okay, type an answer. At what maximum height does this object have at the other side? Age. Good. It's going to have the same age as this, right? This age and this age are going to be the same. Okay? So again, once it reaches this point, right, it's going to have just potential energy. It's only going to have PE, right? Potential energy, or gravitational potential energy. So that means that the total energy, right, this is going to be mgh, is the same as this mgh. It's not like the mass is going to change, right? The mass here and the mass here are the same. Gravity is not going to change, right? And if they have to be equal, that means the height also has to be equal. Okay, since there is a conservation of energy, the maximum height that this will reach should be the same height, assuming there is no friction. Okay, so similarly with like a ball, right? If you guys have a ball, like a bouncing ball, and like let's say you drop it from a certain height, the maximum height it will reach after it bounces up should be the same height as when you drop it from. Okay, again, there will be energy loss either through sound or friction, right? But assuming there is no energy loss, the height of the ball should be at the height of where you dropped it, right? It will never go above that. Okay, so this is super important to understand. When you drop a ball, right? When you bounce a ball, even you just like drop it and let it bounce, the ball should never go past where you dropped it, right? Because that will go against the idea of conservation of energy, right? That never ever happens. Okay, there is no ball, right, that bounces and goes past where you dropped it from. That doesn't happen. Okay, so that's basically what energy is. As long as you know these equations, I guess you're gonna be fine. Okay, energy is pretty easy, and the idea of energy is super cool because it makes a lot of problems easier, right? So again, we've talked about this before. When I have an object, right, at a height, let's say 5, and a mass of like 3 kilograms, okay? And so let's say this object is going to go down. I'm just going to drop it. So we know the total energy here is just potential energy, okay? So if we're going to solve for it, it's going to be mgh, which is mass, which is 3, gravity is 10, height is 5. So that's going to be 30 times 5, which is going to be 150 joules. Okay? Unit for energy is joules. So right here, when it falls down, when it's about to hit the ground, we know that the total energy will not be just potential energy. It will be kinetic energy. Meaning that 150 joules becomes kinetic energy. Right? So we're just going to solve for it. 150 is equal to kinetic energy, which is 1/2 mv squared. So it's going to be 150 is equal to 1/2. M is 3. Right? I'm looking for velocity. And then we're just going to solve for it. Times u is 300. 3v squared divided by 3 is 100. Oops. And then square root of 100 is going to be 10. So the velocity of this object over here is 10 meters per second. Okay? And that's pretty easy, right? So what you had to do before, because you can solve this problem in two ways. You can solve this problem using kinematics, right? Yeah, so I can solve this problem using kinematics. I know like the initial velocity is 0. I know gravity is going to be -10, and I know that the change of x is going to be 5. So I'm going to use one of the kinematics equations to find final velocity, right? But I can just use kinetic energy or the conservation of energy to be able to solve the problem, which I believe is a lot easier. Okay. Yeah, that should be it, at least for this part of energy. Okay. Right. So now, with the time given to us, we should have time for, and we talked about this last time already, about simple harmonic motion. Okay. So simple harmonic motion is typically going to be observed through a spring or a pendulum. Oops. typically like ideal springs and ideal pendulums, right? We're not at a level where we can do where we can work with non-ideal springs and non-ideal pendulums, right? We're only going to work with ideal springs and ideal pendulums. Okay, so the idea of simple harmonic motion, the equations that we're going to need to know, right? Let's work with spring first. Is first Hooke's law, right? So Hooke's law understands that F is equal to negative kx, right? So the force of a spring is equal to spring constant, the spring constant, and change of x is displacement. All right, that's fine. So that's the first thing that we have for, I guess, the spring, right? That's forces. And then if we have like this, we also have the elastic potential energy. Okay, so this is elastic potential energy is equal to 1/2 kx squared. Okay, important things about springs. Okay, so pendulums. Oh, sorry. Let's continue with springs. Okay. So another important equation for springs is the idea of the period of oscillation. Okay. So remember what happens with springs, right? Is it goes right, left, right, left, right, left, and it's gonna keep going in that motion forever and ever and ever, right? So we're going to have the concept of oscillation, and we're going to have to figure out like period, meaning the time it takes for it to complete one cycle. Okay, so again, the time for it to take to complete one cycle is going to be found using this equation: 2 pi squared of m over k. Okay, so the period of the spring, this is going to be mass and spring constant. Yeah, so to find the period of a spring, we're going to utilize this equation, right? And period is again the time it takes for one cycle to happen. I'm just going over the equations right now. I'm like, we'll explain this. We'll try to explain this like with the time that we're given, or the one last day we're given, I guess, on Tuesday. Okay, so now we're going to do the pendulums, right? So pendulum, okay, we're only going to have like this equation, right? So with the idea of a pendulum, we're going to have the period is equal to 2 pi L over G, right? This is going to be the length of the string, and then this is going to be gravity, acceleration due to gravity, okay, which is 10. Okay, so what is the important thing here is like for the period of oscillation, right? What dictates the period of oscillation for a pendulum is just going to be the length of the string and acceleration due to gravity, right? Since if we're on Earth, G is never going to change, right? But the length will, right? So if we have like the only thing that really dictates how long one cycle to happen in the pendulum is going to be how long is my string, right? It doesn't matter how heavy the pendulum is or how heavy the object at the end of the pendulum is, right? The only thing that matters is how long is my spring, or how long is my string, right? It doesn't even matter where you start from. Are you starting from over here, or are you starting from over here? It doesn't matter, right? The only the time for it to go and come back is only dictated by the length of the string. Doesn't matter about this angle. Doesn't matter how heavy this ball is. The only thing that matters is the length of the string. Okay. So similarly, in the for a spring, right? For a spring, the only thing that matters is the mass that's moving, the mass of the object moving, and the spring constant. Okay. Those are the only things that matter. Okay, super duper important to understand when we're talking about simple harmonic motion. Okay. Also, I guess let's look at like a pendulum. Okay. So, remember a pendulum over here, it's going to have, again, it's just going to have potential energy, right? But then when the object is over here, it's going to have kinetic energy. But when the object is like right in the middle, it's going to have potential plus kinetic. Okay, just know that. that's pretty basic. Um, Also another thing. Sorry about totally forgot. So remember, we also have something called frequency. Frequency is how often does a cycle happen every second, right? How many cycles happens every second, and that's going to be 1/t. So period and frequency are inverses of each other. Okay, that's basically it. So these are just like, I think we're still missing gravity. I think we're only missing gravity and circular motion, right? But we're going to do that on Tuesday along with like graphs. So that's going to be it for today. Important thing though is, what else? Is please watch like the videos that I'm posting. I know there's going to be a lot of them because I'm going to put in more, and I apologize for that. But it's like 1 week left. But it's going to, please watch those videos, especially the ones about like the AP exam, and please like keep watch of like emails sent to you by College Board, right? So two days before your exams, so whether it's AP US History or my physics exam, make sure that you get an email by College Board, right, that tells you what to do. Okay, so make sure that like you know what to do on the day of the exam. Okay, if you have any questions, please ask. I'll try to find an answer for it. I personally recommend you guys to take it on the computer. And this is why, right? So if you take it on the computer, you can have like the formula sheets on your phone. Okay? Like, I mean, just make sure, like, if I were you guys, I would have like two devices to work with, right? I would try to have two devices to work with. Although, the idea with a phone, so I guess a phone is fine because you would have to upload it, right? So you would have to take a picture and upload it. So I guess a phone, but make sure that you have like, so I guess it doesn't really matter, but make sure that you have like two things to work with, right? Either with two phones or a computer in the phone, laptop in the phone, doesn't really matter. But make sure you have like two devices to work on, okay? Just in case, right? Any other questions, guys? But please, like, if you think of anything between now and like the weekend, please let me know. Okay, hold up. I'm going to like Andrew, Angela, Esmer, and Priscilla. Yeah, you guys haven't like finished your registration, so please like, and the people I called out, please send me an email of like a bill with your address on it, whether it be a light bill or like a utility bill, water bill, right? As long as it has your address on it, like as long as it proves that it's like, it can even be like your parents' license. Please send me an email like as soon as possible, right? So I can so we can do your registration, because we really need those for your registration for next year. So again, that's Andrew, Angela, Esmer, and Priscilla, at least from the ones in this list. And Evelyn. Sorry. Evelyn, you too. Please send me an email as soon as possible. Please, those people that I mentioned. All right. That's it for today, guys. Bye. Thank you so much. Have a nice rest of the day.